Morning, grade 10s. Welcome to your fourth lesson on probability. Today we're going to be looking at a few new terms. The first term we're looking at is mutually exclusive. Exclusive meaning excluding, and a Venn diagram set with mutually exclusive means they have nothing in common. There's no overlapping, there's no intersection. So A would be a circle on its own that doesn't intersect or overlap with B being a circle on its own. And we call this mutually exclusive. They exclude one another. Okay? So when I have mutually exclusive, the probability of an intersection, remember this being and, A and B, is 0. Can you see there's no outcome where they would both have the same results? So the probability is impossible. It's impossible for them because they don't overlap. And then the probability of A or B, meaning a union, is everything in total. So the whole of the whole of A plus the whole of B. And this time, unlike yesterday, we don't have to subtract an intersection because there is no intersection. So it won't be counting something double. So it's just the probability of A and the probability of B together give you the union. And this is mutually exclusive. What is an example of mutually exclusive? It would be like if I had a deck of cards and I asked you to put all the queens into my blue circle and all my kings into my red circle. So I'd have a queen of hearts, a queen of diamonds, a queen of spades, a queen of clubs. And I'd have a king of hearts, a king of diamonds, a king of spades, a king of clubs. And I said to you, what is the probability of getting a queen and a king? Do you see the chance of me pulling out one card that is both queen and king is impossible? So what I mean is when I pull one card, it could never be a queen and a king. It can either be a queen or it can be a king. It can't be a queen and a king at the same time. And so they're mutually exclusive. So the next word we're going to talk about is an exhaustative event. So not like the exhaust on your car, but rather, or your parents' cars, because you don't drive yet, but rather when you exhaust something, you tire it out, it's the end of it, it's finished. So if I gave you a sample space with the letters A, B, C, D, E, F, G, an exhaustative event means that if everything in my sample space falls into my intersections. Now, they can be mutually exclusive and still have the whole sample space inside. So if I said A was made up of A, B, C, and D, I would have A, which would be A, B, C, and D, and B would be E, F, and G. Do you see how nothing else remains in my sample space? Because my sample space was made up of A, B, C, D, E, F, G. And I've got all of those inside one of my events. So this is an exhaustative event. It's used up the whole sample space. Now, very important. In exhaustative events, the union of the exhaustative events always equals 1. Okay? How come? What does 1 stand for? 1 stands for 100%. And you agree that when we have a union, it's the total altogether, right? So when we have an exhaustive event, we've used everything. So the union must always come to 1 or 100% because I've 100% used up my sample space, even though they don't overlap. So now an exhaustative event can also look like this. Exhaustative events can also overlap. They can also use up the whole sample space, even with an intersection. So now I've just changed it that they have D in common. So D would go in my intersection, and my event A would just be A, B, and C, and my event B would be E, F, and G. I've still used up my entire sample space. I've exhausted all my options, okay? And the probability of their union in total is still 100% because I've got 100% in each of my circles. I don't have anything remaining in my sample space. So it must still equal to 1. And the last word you're going to learn today is a complementary event. And a complementary event is when it's exhaustive and mutually exclusive. So what do I mean by exhaustive? I mean that there's nothing that lies outside of my event, so there's nothing extra in the sample space, and it must be mutually exclusive, which means they have nothing in common. So in my two events, event A, I put 7 yellow triangles, and in event B, I put 8 red rectangles. Do you see how I've used up my entire sample space? I don't have any other shapes lying on the outside, okay? And also they're mutually exclusive because they've got nothing in common. These are yellow and triangles, and these are red and rectangles. So these are complementary events. And with a complementary event, do you agree that because it's exhaustive, the union, the total, must come to 1 because I've used 100% of my sample space in total? And then the intersection, what they have in common, always comes to 0 because it's impossible that these two things have anything in common. So let's try both out. What is the probability of A or B, meaning everything in total? So I want, firstly, the probability of A, which is 7 out of a total of 15, because I've got 15 shapes in total. 7 out of 15. And what is the probability of B? It's 8 out of 15. And what happens? I've got this together with this, because they're in union. So I've got the 7 and the 8, and what do I end up with? The probability of A or B, the union, 7 over 15 plus 8 over 15 is 15 shapes out of 15 shapes, which gives me 1. It's exhaustive. I've got nothing on the outside of my sample space. And now let's just check out their intersection. So I take the probability of A, which we said is 7 out of 15, and we take the probability of B, which we said is 8 out of 15, but none of these things are made up of anything in common because these are 7 yellow triangles and these are 8 red rectangles. There's nothing in common. Remember, the intersection is what they have in common. Even if I had to dot my circles and see where they overlap, the probability of A is simply here, so it gets a dot, and the probability of B is simply here, and it gets a dot. Nowhere do they intersect or do they have anything in common. So the probability of their intersection, where do they overlap or what do they have in common, comes to 0. They have nothing in common. So let's quickly refresh. Exhaustive means that there's nothing in my sample space. So when it's exhaustive, my union always comes to 1. It's 100%. Mutually exclusive means they don't overlap. So when something is mutually exclusive, it means my intersection always comes to 0. And complementary is when these two things happen together. So exhaustive, this happens. Mutually exclusive, this happens. When it's complementary, they both happen because complementary is both of those things at the same time. Just to explain this further, if I had to give you this Venn diagram with 3 circles, they're ovals, and I'm just talking about colors, I'm not wanting to see if they've got their shapes in common. So I've got 1 yellow, 1 red, 1 blue, and 1 green. And my question to you is this a complementary event? And I hope your answer is no, because it is not exhaustive. There's a green floating around here in my sample space. It may be mutually exclusive, which means that their intersection comes to 0, but it's not exhaustive because their union doesn't come to 0. Let me show you. If I had to have the union of the probability of yellow, which gives me 1 out of 4, right? The probability of red, which gives me 1 out of 4 because we've got 4 colors, and the probability of blue is also 1 out of 4. Do you agree that the union between these 3, the probability of yellow or red or blue, would be this and this and this. I don't have to subtract anything because they're mutually exclusive. They have nothing in common. So in total, I've got 1 over 4 plus 1 over 4 plus 1 over 4, which gives me 3 over 4. And that just proves to me it's not exhaustive. Exhaustive, a union, must always be 100% of my sample space is used. So when would it be exhaustive and mutually exclusive? If I removed green from my sample space and I was just left with this. My options for getting the probability of yellow would then become 1 over 3. My probability of getting red would become 1 over 3. And my probability of getting blue would be 1 over 3. And then their union is what? 1, 2, 3 options out of a possible 3 out of a possible 3 options. And I end up with 1 or 100%. So 100% of my sample space has been used, so it's exhaustive. Are these mutually exclusive? Yes, they've got nothing in common. So what can you tell me about them being complementary? It's exhaustive and mutually exclusive. So their union always comes to 1 and their intersection always comes to 0 because nowhere do they overlap. So it's impossible to get yellow and red or yellow and blue or yellow and red and blue. There's no intersection between them. So it's an impossible event. So your first example for today reads like this, is if the probability of A is 0.3, the probability of A is 30%, okay, and the probability of B is 40%, where A and B are mutually exclusive. So that's the next thing we've learned, is that they're mutually exclusive. So when I draw my Venn diagram, I've already drawn it up for you, exclusive. Remember, this means that they don't overlap. So the probability of A stays 30% in the circle because I don't have to remove the intersection. And the probability of B stays 40% because, again, I don't have to remove an intersection. The first question says, determine the probability of A and B. And I hope you agree, they have nothing in common. We're told they're mutually exclusive. So the probability for A and B immediately you can see is 0. It's impossible to get A and B at the same time because they're mutually exclusive. The next question asks, what is the probability of A or B? Their union. Now remember, is this exhaustive? 30 and 40 gives me 70%. That means 30% is still outside here in my sample space. So it's not exhaustive, so it's not complementary. So that means this does not come to 1 because it's not complementary. I need to exclude the 30%. The union is everything they have in total minus the intersection because I can't count the intersection twice. So everything they have in total, the probability of A, which is 30%, and the probability of B, which is 40%. They don't have an intersection, so the probability of A or B is these things in total, their union, they're coming together, and that leaves me with 70%. And lastly, it asks for the probability of not A or B. So this is really easy because if this is A or B, not A or B would just be what remains on the outside of my sample space. So the probability of not A or B would be 30%. So those are my 3 answers. A comes to 0, B comes to 70%, and C is 30%. Example 2 reads as follows. A and B are mutually exclusive events, meaning they don't overlap. So I've got event A and I've got event B. It says the probability of not A is 0,3, which I've labeled as 30%. And the probability of their union is 80%. So as soon as we see that their union is 80%, are these events complementary? And the answer is no. Because remember, a union, if they're complementary, must be that I've used 100% of my sample space. I haven't used 100% of my sample space. I've only used 80%. So that means there must be 20% on the outside. So it's not exhaustative. It's only mutually exclusive. So the probability of not A is 30%. So remember, A is everything that lies on the outside. Let's just do a mathematical equation. Remember, not A equals 1 minus the probability of A. We've discussed that formula. So if not A is 30%, what is the probability of A? Solving for this, we swap our equation around and we get 1 minus 70% would give me the probability of A. And the probability of A is therefore 100% minus 70%, which leaves me at 30%. So the probability of A is 30% on its own. Whoopsie, I've made a mistake. I'm thinking ahead of myself. Rearranging the equation should be 1 minus 30%, not 70%. So therefore my answer is 100% minus 30%, and that's where my 70% is. So the probability of A is 70%, and because they're mutually exclusive, there's no intersection, that 70% belongs solely to A. So A is 70%. Okay? If their union together, A together with B comes to 80%, do you agree that my event B here must be 10%? Because 70 plus 10 gives me 80%. And that's the first question. It says determine the probability of B. So mathematically, I would show the probability of A is 70%. And then I would say that the union minus the probability of A would give me the probability of B. So the probability of B, therefore, is the union of 80% minus the probability of A, which is 70%. These are supposed to be percentage signs over here, sorry. So therefore, the probability of B lands at 10%. And I hope you can see it in the Venn diagram. And the second part of this question says, explain why A and B are not complementary. Well, they're not complementary because it's exhaustative. Remember, when we have a union, the probability of A or B always gives me 1. But in this case, my union gives me 80%. Therefore, the probability of not A or B must be 20%. Because it's not included in my sample space, so not the union, everything else except for the union. So therefore, it's not complementary because it's only mutually exclusive. It's not exhaustative. And remember, complementary must be both mutually exclusive and exhaustative. And your third example for today says that the probability of A is 0.6. I'm just going to write 60% because that's what makes sense in my brain. And the probability of B is 50%. It says, prove that A and B cannot be mutually exclusive. Cannot be mutually exclusive means that A and B must have an intersection. So A and B must have something in common. And why would this be the case? Okay. Well, firstly, remember, if they're mutually exclusive, the probability of A or B means I take the probability of A plus the probability of B. Because when they're exclusive, there's no intersection. So it would just be all of A plus all of B. I don't have to subtract an intersection. And let's just work it out mathematically. If we've got 60% plus 50%, we end up with 110%. And that's impossible because my sample space is only 100%. So that just proves that they cannot be mutually exclusive. There has to be an overlapping because obviously I've added something twice. So these two events overlap, they've got an intersection, they're inclusive. If I had to draw this in a diagram, what would be part of my intersection? How much have I exceeded 100%? I've exceeded it by 10. I've obviously counted 10 twice. So there's a 10 in the middle. That means the probability of only A, this on the outside, is 50%. And the probability of only B on the side here would then be 50 minus 10, which would be 40%. And then this would be complementary because it's exhaustive. There's nothing on the inside. Okay? No, it wouldn't be complementary because there's an overlapping. So it's just that they have an intersection, that they're inclusive. It's not mutually exclusive. And that is what my diagram would look like. So now grade 10s, you're going to go and do exercise 4 for homework. I know that this is a difficult section for you, but probability takes practice, and practice doesn't necessarily mean perfect, but it does mean progress, and that's what we want. We just want to keep on progressing. Have a good day, grade 10s.